Hello everybody. We have been talking about writing the electronic configuration of elements. Now in class 9, you have been familiar with writing the electronic configuration using the Bohr's model of an atom, where an atom is made up of circular orbits or shells denoted by K, L, M, N shells. Now each shell had also a maximum number of electron capacity, where we had K shell having the maximum capacity of 2 electrons, L with 8 electrons, M having the maximum for 18 electrons, and N for 32 electrons. Now we are going to upgrade ourselves into writing the electronic configuration in S, P, D, and F format. Now each shell can be divided into subshells written by using the adjoining letters S, P, D, F. Each subshell also has a maximum capacity of filling in an electron. So that means S can take 2 electrons, P can take 6 electrons, D has a maximum capacity of 10 electrons, and F has 14 electron capacity. Now this is as far as we know. Now in class 9, we were also introduced to the first quantum number called principal quantum number, denoted by n, which could take integral values of 1, 2, 3, etc. So we also assigned the principal quantum number values for our designated shell, where K shell had the value n equal to 1, L had n equal to 2, M had n equal to 3, etc. Now we know that n is the first quantum number, which is called the principal quantum number. Now let us understand what n actually symbolizes. The principal quantum number n denotes the energy of the shells. Now what that means is, for the shell n equal to 1 has lesser energy than the shell n equal to 2, and so on. Now again, in a visual context, let us try to relate it to the Bohr's model of an atom. So let us draw the Bohr's model, where capital N denotes the nucleus of an atom. And since I'm talking about the Bohr's model of an atom, I should be drawing circular orbits to denote the shells. So this is the first shell, this is the second shell, and this is the third shell. Now again, let me denote it with the values of the principal quantum number. First shell gets n equal to 1, the next gets n equal to 2, the third gets n equal to 3, and so on. So as I just said before, n corresponds to the energy of the orbital. Now what that means is, an electron which is there in n equal to 1 shell has lower energy than an electron which is there in n equal to 2 or n equal to 3 shell. Now another interesting thing that we can see about n is, as n increases, the size of the atom also increases. That is, the distance of the valence shell from the nucleus of an atom is denoted by the principal quantum number as well. The distance of the valence shell, or the size of an atom, is basically measured from the center of the nucleus to that of the outermost shell, or the valence shell of an atom. That is, to summarize, as n increases, the distance of the orbit of the atom from the nucleus also increases. Now here we are moving on to the next quantum number. So the second quantum number that I am going to introduce to you is denoted by the letter L, which is called the azimuthal quantum number, or the angular momentum quantum number. Now, azimuthal quantum number denotes the shape of the orbital inside specific shells. So when we talk about the spdf orbital, essentially we are talking about the locations in space where it is most likely for us to find an electron. Now these locations of electrons correspond to various values of the azimuthal quantum number L. That is, S, P, D, and F have specific values of L assigned to it, and that denotes a specific shape. So, S orbital is denoted by L equal to 0, which is spherical in shape. P orbital gets the value L equal to 1, which denotes a dumbbell shape. D orbitals have the value of the azimuthal quantum number as L equal to 2, and they generally are clover shaped. Now, these shapes can vary across their Cartesian planes. That is when we look at it from the x, y, or z axis. But essentially, this is what they look like. F orbital has the value of L as L equal to 3. The F orbital is quite difficultly shaped, so I am not going to be talking about it. So right now, we have talked about two quantum numbers. The principal quantum number, which talks about the energy of a shell, and the azimuthal quantum number, which talks about the shape of the orbital in the shell. Now, the next question is, how are these two related? Let us now discuss the relationship between n and L. L can take up to n minus 1 values. So, what does that mean? For the first shell n equal to 1, L can take n minus 1 values. Then L takes the value of 0. And the value L equal to 0 corresponds to the s orbital. Similarly, for n equal to 2, L can take two values, either L equal to 0 or L equal to 1, which correspond to the s and the p orbital. For n equal to 3, L can take L equal to 0 value, which is S, L equal to 1 value, which is for P, and L equal to 2, which is for D. For n equal to 4, you will have 4 values of L, where all the S, P, D values follow, and L equal to 3 for F. Now, here's an interesting aspect to look at. If you see for n equal to 1, L also has 1 value. For n equal to 3, L also has 3 values. Suppose n is 20, then n would have 20 values from 0 to 19. Now let us go about writing the electronic configuration of an element. First, we start building up the orbitals. We know that we start writing the electronic configuration from the lowest energy level. So we always have to start from n equal to 1 and then keep moving into subsequent values of n. For n equal to 1, we have 1s. For n equal to 2, we have 2s and 2p. N equal to 3 has 3s, 3p, and 3d. Now, because we saw that the value of n would correspond to the total number of values for L. Again, for n equal to 4, we would have 4s, 4p, 4d, and 4f. These orbitals also have a maximum capacity of electrons that can be filled into it. So, for s orbitals has the maximum capacity 2 electrons, p 6 electrons, d can hold up to 10 electrons, and f can hold 14 electrons. Now, when we start writing the electronic configuration, we start from the top and go diagonally down. So, first comes 1s, then 2s. After 2s, it is 2p and 3s. After this is 3p and 4s, and so on, until you get the needed orbital count. Now let us start writing the electronic configuration of elements. I will choose the simplest atom that we have, hydrogen, atomic number 1 and mass number 1. And this is how it appears in the periodic table. Now, to write the configuration of neutral atoms, we know that the atomic number is the number of protons, which is also equal to the number of electrons. Hydrogen in this case is neutral because I haven't denoted any charge onto it. So let us try writing the configuration of hydrogen. First, we start with 1s, and s can take 2 electrons. But we just have to fill 1 electron. So we write 1s1. Now, here are a couple of things you might want to look into. We started with the values of the principal quantum number and the azimuthal quantum number. N is defined by the first number, and it defines the energy of the orbit as well as the distance of the orbit from the nucleus. Now, looking at S, we know spdf have different values of L. So, for S in particular, we have L equal to 0. The exponent indicates the total number of electrons filled in the particular orbit. Now let us try writing the configuration for higher atoms. Taking the element potassium with atomic number 19. Since the atom is neutral, potassium also has 19 electrons. So let us write the orbital layout. First is 1s, then 2s, 2p. Then we have 3s, 3p, 3d, and 4s, 4p, 4t, and 4f. Now this is enough for potassium, and we know that the s orbital can take 2 electrons, p can take 6, d can take 10 electrons, and f can take 14 electrons. Now let us start filling this. First we take 1s, and we have 1s2 because it can take 2 electrons in total. Then we go on to 2s. Again, s can take 2 electrons, so we have 2s2. Then we go into 2p. P can take 6 electrons, so 2p6, and then 3s2. Now let us have a quick check on how many electrons we have already accounted for. So if we add the exponents 2 plus 2 plus 6, that is 10 electrons, and then adding 2, it becomes 12 electrons. So now to fill the remaining electrons, after 3s, we go on to 3p, and we get 3p6. So now we have 10 electrons here and 8 electrons here. So we have filled 18 electrons. Moving on, after 3p, it is 4s. And it gets the last electron, making it 4s1. Using this configuration, you can tell the valence shell and the number of valence electrons as well. How do we do that? All we have to do is find the highest value of the principal quantum number, as n denotes the shell. So here we have 4s as the last orbital, and n equal to 4 is the valence shell. Now, how many electrons in the valence shell? We see n equal to 4 has only s orbital, which has only 1 electron. So number of valence electrons is 1. Now to write the electronic configuration of an ion. So for the configuration of potassium ion, we know that the electrons for potassium atom is 19. But for potassium ion, which is positively charged, it has lost 1 electron. So whenever we have positive charges, all you have to do is subtract the charge number from the atomic number. So for potassium ion, we end up with 18 electrons. You can try writing the electronic configuration on your own. I will set the orbitals the same way. Now to start writing, we know we start from 1s, and s can take 2 electrons, while p can take 6 electrons, d can take 10 electrons, and f can take 14 electrons. So again, let us begin with 1s, and we have 1s2. Next, 2s2. Then moving on to 2p and 3s, we have 2p6 and 3s2. Now, if we count the number of electrons here, then it is 2 plus 2 plus 6, 10 electrons, and 2 electrons, making the total of 12 electrons. Now we have to account for 6 more electrons. So after 3s, it is 3p, and then it becomes 3p6. Now, if I were to ask you about the valence shell, you would have looked at the maximum value for the principal quantum number. In this case, the maximum value for n would be 3. So we have n equal to 3 as the valence shell. Now, how many valence electrons? You would be wrong if you had just considered this, because we can see that n equal to 3 shell has both 3s and 3p. So the number of valence electrons is found by adding the exponents of all the electrons in the valence shell. And the number of valence electrons would be adding the electrons in both 3s and 3p, which is 2 and 6, making a total count of 8 electrons. Now, this is also a complete octet, having the nearest noble gas configuration. Now, let us try another example. Suppose I have to write the electronic configuration of silicon with atomic number 14. You can pause the video and go about it yourselves. In the meantime, I will set it up the same way. Now, let us start writing it. First, it is 1s, which is 1s2. Then we on to 2s, so that goes 2s2. Then on to 2p and 3s, which is 2p6. Now, before we move on, I will just count the number of electrons. We have 10 electrons which are already done. Now to fill 4 more, because the total number of electrons here in silicon atom is 14. So after 2p, we have 3s, where you get 3s2, as s in general can take on 2 electrons, and then we have 3p. Even though p can take 6 electrons, we don't need that. We only have 2 more electrons to fill, so that becomes 3p2. Now to quickly verify our count, we have 2 plus 2 plus 6, which is 10 electrons, and 2 plus 2, 4 electrons, and the total electron count is 14 electrons. Now, let us try to apply what we've learned about quantum numbers. Consider the outermost orbital 3p3. Can you figure out the values of n and l? So we know that the first numerical value corresponds to the principal quantum number. So n equal to 3. That is the third energy level, or the M shell. P orbital gives us the value of L, which is the azimuthal quantum number. We also know that for p orbital, the value of L is equal to 1. And the exponent 3 refers to the total number of electrons in that orbital. Happy learning!